Hello and welcome, friends. Today I've got a PE Civil Review problem for you guys. This one's about catenary cables. Should be a lot of fun, so let's hop right into it. Alright, so boom. We've got two towers that are located on ground level, 100 feet apart. They support a transmission line with a mass of 2 pounds per feet. The midpoint sag is 10 feet. So let's draw a little diagram for this. We've got tower number 1, and then tower number 2. They are both 100 feet apart. I'm going to make this length L. So L is 100 feet. Then we've got the transmission line that sags down here. So this one has a distributed load on it. The distributed load is going to be acting downward on the cable, and that is downward this way. And that's going to have a distributed load of 2 pounds of mass per foot. Let me get rid of this so I can clean it up. Hopefully I don't get anything else. There you go. And the midpoint sag is 10 feet. So the sag right here, that distance, that's S, and that is going to be 10 feet. Now what are they asking from us? The midpoint tension is most nearly A, B, C, or D. Now, the midpoint tension. If we were to cut a line right down here in the middle, the only tension in the line would be acting vertically. So this tension would be right here, acting vertically through the middle of this transmission line. And that's what we're looking for. So to get this done, we're going to look through our handy dandy civil reference manual, the CRM, and we look at equation 4170, which tells us that H, which is the horizontal component of tension in the cable, is equal to the distributed load multiplied by C. Now what's C? The C is the parameter of the catenary. So this vertical height, this total vertical height here, we could call it Y. And then we have this height, S, which is the sag. C is just the difference between these two. That's C. Now, one thing to note is that C, in this example, I have it basically going down to the ground level, but Y is not a height of any physical location. It's just the height to a reference line. With that being said, C is the only parameter here that we don't know. So we need to find C. Now, how do we do that? Go back to our civil reference manual and look up equation 4165. This one shows that Y at distance of X is equal to C multiplied by the hyperbolic cosine of X over C. Great. So the only two parameters here that we don't know is Y and C. So we're gonna go about this by finding C. So first step here is to see that Y, this Y as we can see here, can also be substituted for S plus C. So let's go ahead and do that. So S plus C is equal to C times the hyperbolic cosine of X over C. Now if we multiply both sides by c, we will have s over c plus 1 is equal to the hyperbolic cosine of x over c. Now let's plug in the numbers that we know. We know that s is 10. 10 over c plus 1 is equal to, oh, let me put this hyperbolic here, the hyperbolic cosine of x over c. Now what's x? X is the horizontal distance to the midpoint. In this case, x is L over 2, which is 50 feet. Let's put that in here, 50. All right, so now we have this function here that we have s, we have c at the bottom here, also c at the bottom here. Now that's tough to solve for. So to solve for it, we're going to have to go through an iterative process. So to do that, we're going to make a table. All right. We'll have c on one side, then the hyperbolic cosine of 50 divided by c, and then 10 over c plus 1. So basically what we're going to do is we're going to pick a c, then we're going to find out what the cosine, what this side gives us for the that value of c, and find out what this side gives us for that value of c, and then try to adjust that c number until both sides are we want to get to a point that they're both equal to each other, but as long as they're really close to each other, that works for us. So let's start off with 50 feet. So I'm going to assume that this c here is 50 feet. Grab my calculator. So with that c being 50 feet, this hyperbolic cosine 50 divided by 50 is 1.543. Okay. And then on the other side, this 10 divided by 50 plus 1 is going to equal to 1.2. Okay. So we got 1.543 on one side and 1.2 on the other side. Kind of close, but not close enough. Let's keep going. Let's try the next one. We're going to try go higher. 100. Let's try 100. Okay. So doing 100, the hyperbolic cosine of 50 divided by 100, that gives me 1.128. Now on the other side, 10 divided by 100, which is 0.1, plus 1 is going to be 1.1. Getting closer. I'd like to get a little bit more closer, a little bit closer for me. I like having it closer. So let's try 125. Okay, the hyperbolic cosine of 50 divided by 125 is 1.081. Now 10 divided by 125 plus 1 is equal to 1.8. Nice. 1.08. That's good. I'll accept that. So in this case, we can conclude that C is equal to 125 feet. Always going to keep our units with us. That's awesome. So now we have C. we can go back to equation 41.70 and solve for H. So the horizontal component of tension in the transmission line is equal to W times C, which is equal to 2 pounds of mass per foot multiplied by 125 feet. We also need to convert it from pounds of mass to pounds of feet. So good for us in the US units, 1 pound of mass is the same as 1 pound of force. But we do need to note that if we were using SI units, this wouldn't be the case. In this case, we would have to multiply it by 9.81, but in US units, that's not an issue for us. So 2 times 125, that's 250 pounds of force. Okay, so hopefully that is one of our multiple choice answers. Yes, it is, right here. So the answer is B.